All right, jumping right off of our last video, we're going to continue with this idea of reviewing the necessary stuff that we need to calculate vapor pressure lowering, okay, which again falls under one of our colligative properties. Now, we talked about some useful equations last time. For the liquid, we saw that our mole fraction of component I in the liquid was equal to our moles of component I in the liquid over our total number of moles. Again, moles of component I over moles total in the liquid gives us our mole fraction of that component in the liquid. We could also calculate our partial pressure of component I in the vapor by looking at the liquid terms. Okay, so we can get our vapor pressure of component I, our partial pressure of component I, which was equal to our mole fraction of component I times our pure component vapor pressure of component I. We could also do the same sort of thing for our vapor, right? Where we had the mole fraction of component I in the vapor was defined as the mole fraction of component I over our total number of moles both in the vapor. We can find our partial pressure of component I in the vapor by taking our mole fraction of component I times our total pressure in the vapor. And we could also calculate our total vapor pressure by simply adding up all of our partial pressures in the vapor. Now that equation, I didn't mention this last time, that's called Dalton's law of partial pressures, okay? We also were able to relate our vapor and our liquid by using Raoult's law, which said that the mole fraction of component I in the liquid times our pure component vapor pressure of component I was equal to our mole fraction of component I in the vapor times our total vapor pressure, right? We also had a couple of useful relationships, which said that the mole fractions, if we add up all of our mole fractions in the liquid, we should get 1. And if we add up all of our mole fractions in the vapor, we should get 1. One other thing that's kind of useful is if we take a look at our partial pressure definition in terms of the vapor, right? We saw that our partial pressure of component I was equal to our mole fraction of component I times our total pressure. So we could also, if we wanted, determine our mole fraction of component I by simply taking our partial pressure of component I and dividing it by the total, right? And that just sort of makes sense. The part of the gas that came from one component over the total should give me my fraction of that component in the vapor. All right, so now we're ready to start looking at a couple of examples. All right, now these are going to be on slides 19 and 20, and depending on which version you're looking at, you will have one of them will correspond to a single volatile component, and one of them will correspond to 2 volatile components. We're going to start with the one that corresponds to 2 volatile components. Okay. Now, this example says that a solution of benzene, which is C6H4, and toluene, which is C7H8, has a mole fraction of 0.25, okay, a 0.25 mole fraction of benzene, okay? The vapor pressures of pure benzene and toluene at 25 degrees C are 94.2 torr and 28.4 torr respectively. From this, we should be able to calculate first our vapor pressure of each component and the total pressure. Now, when you're looking at some of these types of problems, the first thing that you want to do is identify the type of problem. We know that we're looking at mole fractions and volatile components, so we're probably going to be dealing with a vapor pressure lowering problem, okay? So that means that it's going to be using some or all of those equations, okay? First thing that you're going to want to do when tackling these problems, step 1 is going to be to identify your knowns, the things that you know, all right? Now, right off the bat, we know that the solution, right? So they're talking about the liquid. The solution has a mole fraction of benzene that is 0.25. Now, since we're talking about the solution, we know that we're going to have a mole fraction, which is X, right? Since we're dealing with the liquid, a mole fraction of the benzene. I'm going to use a little b for benzene that's equal to 0.250. Okay, that's my fraction of the liquid or of the solution that's benzene. I also know that my vapor pressure of pure benzene and pure toluene are given by these, right? Now, since it says pure, that's a clue to you that you know that these are going to correspond to our pure component vapor pressures. That's going to be the ones that have the little circles. So we also know that we have pure component vapor pressure for benzene. The one for benzene was 94.2. And we have the one for toluene. I'm going to use a T for that. Let's use a capital T. Yeah, capital T. So that's going to be my pure component vapor pressure of toluene, and that was 28.4 torr. Okay, so those are the three things that they gave me. The next thing that I want to do, step 2, is going to be to determine any possible other mole fractions that we could have. Well, I have the mole fraction of benzene. Well, is there another way that I can find one of my other mole fractions? Well, right off the bat, I know that the sum of all of my liquid mole fractions must add up to 1. Well, there are only 2 components in this particular solution. So I know that if I take my mole fraction of benzene and I add that to my mole fraction of toluene in the liquid, then that should add up to 1. Well, I know that my mole fraction of benzene was 0.25, and I have my mole fraction of toluene, and then that's equal to 1. Well, if I want to find my mole fraction of toluene, I just have to subtract 0.25 from both sides. So that means that my mole fraction of toluene is equal to 1 minus 0.25, or if I do the math, I will get 0.750 as my mole fraction for toluene. Okay, so right off the bat, because I knew it was a binary mixture of 2 components, if I know one of them, I automatically can easily figure out the second one. Okay, then lastly, step 3 is going to be to try to calculate our desired quantity. Our first desired quantity was the vapor pressure of each component. Well, we know that our vapor pressure of each component can either be found by the liquid or by the vapor. Notice that we have a lot of information related to the liquid. Okay, so it's probably a good idea to use our vapor pressure, our partial pressure equation for the liquid. So if I want to find the partial pressure of benzene, it's simply going to be equal to my mole fraction of the benzene, XB, times my pure component vapor pressure for benzene. All right, now all I have to do then is simply take my mole fraction of benzene, which was the 0.25, and multiply that by my pure component vapor pressure for benzene, which was the 94.2 torr. Okay, and when I do that, I get my partial pressure of the benzene that's equal to 23.6 torr. Okay, I can also calculate my partial pressure for the toluene. So to get my partial pressure of the toluene, I'm going to take my mole fraction of toluene times my pure component vapor pressure for toluene. Okay, so in this case, I'm going to take my mole fraction of toluene, which we found to be 0.75, times my times my pure component vapor pressure of toluene, which was the 28.4. Right? Now, doing that, we end up getting that my partial pressure of the toluene is 21.3 torr. All right, so now we have our partial pressure of each component in the vapor. All right, the second thing that this problem asks us for is to calculate my total pressure. Now, we have a couple of equations that have the total pressure in it, but the one that we're going to use is the one which is Dalton's law of partial pressures. In this case, we know all of our partial pressures. So since we know all of the parts, we can add them up to get our total pressure. So in this case, using Dalton's law of partial pressures, the total pressure is going to be equal to the partial pressure of the benzene plus the partial pressure of the toluene. So all I have to do is add my 23.6 to my 21.3, and that's going to give me a total vapor pressure of 44.9 torr. Okay? Now, even though this problem didn't ask us for the mole fractions of each component in the vapor, we can also calculate that. So as a third component that I want you to calculate, I want us to figure out the mole fractions of each component in the vapor. Okay? We have the mole fractions in the liquid, but they are not necessarily going to be the same as they are in the vapor. Liquid and vapor mole fractions are probably not going to be the same. So one way to calculate my mole fractions of each component in the vapor is by looking at the moles of that component over the total. All right, well, we don't know anything about moles, so it's probably not that. Another way to do it would be to calculate it by Raoult's law, right? We have our total pressure, we have each partial pressure. So we could plug in those three to find my mole fraction in the vapor. Remember, Y is going to be our mole fraction in the vapor. Or we could be smart and we could use our mole fraction of component I is equal to the partial pressure of that component over my total pressure. So if I wanted to find my mole fraction of the benzene, all I have to do is take my partial pressure of the benzene and divide it by my total pressure. All right? So one way to do that is I can take my PB value, which was the 23.6 torr, and I can divide that by my 44.9 torr. Okay? Similarly, if I wanted to get my mole fraction of toluene, I could just take my partial pressure of toluene over my total pressure in the vapor. All right, so in that case, I would have 21.3 torr divided by my 44.9 torr. Okay, let me grab my calculator and I will punch that in. So we're going to take the benzene first. We can have 23.6 divided by 44.9, and that gave me a mole fraction of benzene in the vapor equal to 0.526. Okay? Now, since it's a binary mixture, I could go through and I could plug all of that in. Or, since I know that there are only two components, I could again use it for the vapor and just take 1 minus that, and it would give me my mole fraction of the toluene. All right, so I should, if I take 1 minus my 0.526, my mole fraction of toluene should equal 0.474. All right, well, if I plug in my 21.3 divided by 44.9, that gives me 0.474 as my mole fraction for toluene. All right? So as you can see, there's a systematic way to use each of these equations to find different components of our vapor-liquid equilibrium. All right? Now, that was the case when we had two volatile components. Okay? Now, what I mean by volatile is that I have two components that can both go into the gas phase. Okay? Both my benzene and my toluene could go into the gas. They could go into the vapor. Okay? Now, that's not always the case. Right? Imagine that if I took some salt water from the ocean and I poured it into a pan on my stove and I heated it up, right? The water is going to be boiled off eventually, but the salt, it's going to stay behind. It doesn't turn into a gas. I'd have to heat that salt up to like 10,000 degrees in order for that salt to turn into a liquid and then into a gas, okay? The salt, it doesn't boil off, right? And you can see the same sort of thing if you, like, let's say you're making sweet tea or something like that, and you put in your sugar and you heat that up, right? And you keep boiling off that liquid, right? Well, if you boiled that off, the water's going to come off, but the sugar that you put in, that's going to stay behind. Sugar and salt, they're not volatile. They're not going to turn into the gas like the water will, okay? Now, when that happens, right, I'm only going to have a certain number of volatile components, okay? So in that case, right, if I have a mixture of salt and water, the water is one volatile component, okay? But the salt would be a non-volatile component, okay? Now, if you have a non-volatile component, then the mole fraction, then its mole fraction in the vapor is 0. Okay? So for instance, the mole fraction of a non-volatile, an NV component, is equal to 0. Okay? This is going to be very, very important. All right? Now, let's say that we do the example that has only one volatile component, or it has some sort of non-volatile component, right? So in this case, we have a solution of ethylene glycol and water, has a vapor pressure of 7.884 at 10 degrees Celsius. And pure water has a vapor pressure of 9.21 torr. What is the mole fraction of the ethylene glycol in solution? Okay, so going over to our steps for these problems, we know we're going to use these equations, okay, because we're dealing with a vapor liquid problem. Okay, our very first step is going to be to identify our knowns. All right, right off the bat, it says a solution of ethylene glycol in water has a vapor pressure of 7.88 torr. Okay, we're going to leave that alone for a minute. All right. Here we see that pure H2O, I'm going to emphasize that pure H2O, has a vapor pressure of 9.21 torr. Okay, since we're talking about a pure component, we know that we're going to be looking at the vapor pressure with the little circle. Okay, so we know that PH2O 0, that's our pure component vapor pressure of water at 10 degrees is 9.21 torr. Okay, we know that. Now, I'm going to tell you right now, ethylene glycol, this component is non-volatile. Okay, if you get to an exam and you see and you have a question about whether or not something is volatile or not, feel free to ask. Chances are water's always going to be volatile. Okay, but if you need to know a piece of information, either it's going to be listed or you can ask it, whether it be in the chat or you can raise your hand. All right. Now, for ethylene glycol, it's non-volatile. That means that we know that its mole fraction is going to be 0. Right? So we know that Y of the ethylene glycol, I'm going to use EG, Y of my ethylene glycol is equal to 0 torr. Okay? Now, using our relationship up above, we can figure out our other mole fractions, right? We know that we've got a binary mixture of ethylene glycol and water. So that means that our mole fraction of the ethylene glycol in the vapor plus our mole fraction of the water in the vapor has to equal 1. Well, if ethylene glycol's mole fraction in the vapor is 0, then that means that my mole fraction of the water in the vapor has to equal 1. There's no torr on that. There's no units. All right, so we know our mole fraction of the water is equal to 1. The last piece of information that we know from our problem statement is that the solution has a vapor pressure of 7.88 torr. That's telling you that the total vapor pressure, all right, P total in the vapor was 7.88. So P total is equal to 7.88 torr. All right. Now, the quantities that we're looking for is the mole fraction of the ethylene glycol in solution. Okay. Now, we have the mole fractions in the vapor. Okay. But it's asking us about the mole fraction of ethylene glycol in solution. So that's our X, because we're in the liquid, or in our solution of the ethylene glycol. How are we going to do that? Well, we know our partial pressure of water, we know our total pressure, okay, and we know our mole fraction in the vapor. All right, so looking at our equations over here, we want information about the liquid, okay, and we have information about our pure component vapor pressures for the water, okay. So we know this, and we don't know that. All right. Even though we're looking for ethylene glycol, let's solve for something that we can. Okay. So we're going to start by looking at our water. We've got the P of H2O. That's equal to our X, our mole fraction of the water, times, or in the liquid, times our pure component vapor pressure of the water. Now, we know in the vapor that all of the vapor came from water, okay? So, and another way that you can think about this, right? We know that we could use Raoult's law, right? We could say that we have Y of H2O times P total is equal to X H2O P H2O 0, right? That's Raoult's law, right? We know this. This is 1, okay? This was 1. We know that our P total is 7.88. So that means that all of that has to be our 7.88, right? Another way to do that is 1 times 7.88 torr is the left-hand side. Over here on the right, we have our mole fraction of the H2O times our pure component vapor pressure of H2O. We don't know our mole fraction of H2O in the liquid, but we do know our pure component vapor pressure. So we know this. This was equal to our 9.21. Okay, so we can solve for our mole fraction of water. Right, so the mole fraction of water, I simply divide both sides by my 9.21. So that's equal to 7.88 torr divided by my 9.21 torr. And of course, that is going to be equal to 0.855, which is my mole fraction of the water in solution. Okay. Now we can use this relationship right? Because we've got a binary mixture. So I just take 1 minus my 0.855, right? And that will give me my mole fraction of the ethylene glycol in solution, which is equal to 0.145. So as you can see, even though we didn't have enough information to solve for the ethylene glycol directly, we could solve for our mole fraction, and then from our mole fraction, solve for what we didn't know, okay? So sometimes you have to solve intermediate steps, solve for quantities that you can figure out, and then from that, solve for your unknown, all right? That's going to be how we determine vapor pressure lowering. Now, one thing that I wanted to note is the reason that's called vapor pressure lowering is that if you have some non-volatile components, notice how our total pure component vapor pressure was 9.21, okay? But because we had a component that didn't go into the vapor, it actually lowered our total vapor pressure, right? This is 7.88 torr, whereas if we had just had pure water, it would have been 9.21. So our vapor pressure got lowered by adding a non-volatile component, okay? So that's our first colligative property. We're going to tackle some other ones in our next video.